Let's start this video off with a math exercise. What is 15 times 15? To get the answer, you could use a set of divide and conquer rules and conclude it is 225. Let's do that exercise again. What is 15 times 15? You might now remember that the answer is 225. These two strategies are known as generation and recall. Generation because you use a set of rules to generate the answer, and recall because you simply recall the answer once you know it. The same distinction can be made in human motion planning, where motion generation uses internal models to plan a movement for novel situations, and motion recall simply replays a stored movement for known situations. In robotics, sampling-based motion planning is an example of motion generation, whereas motion primitive approaches are rather based on motion recall. The goals of this research project are to compare motion generation and motion recall for motion planning on a commercial mobile manipulation platform, to determine their respective advantages and disadvantages, and to investigate the potential for integrating them. We implement these approaches with lazy RRT and dynamic movement primitives, and we evaluate them with respect to the following criteria: variability, computational load, and generality. Variability. Since motion generation plans from scratch, solving the exact same problem multiple times usually leads to different motion plans. By overlaying 4 resulting reaching movements, for the red dot, we see that the movements differ substantially. This also becomes obvious in the plots of the 3D end effector position, which depict 100 such movements. We see high variability in shape and duration. Because motion recall rather recalls previously executed motion plans, solving the same problem leads to the same result. The 4 reaching movements are so similar it is very difficult to distinguish between them in the video. In the end effector position plots, we also see very low variability. An important difference is also that motion generation does not always yield a valid solution, whereas motion recall does. Computational load. In motion generation, the plan is generated from scratch through a computationally expensive search. For this task, planning time, especially trajectory smoothing, constitutes 35% of the total time. Recalling a plan, on the other hand, has negligible computational cost. Generality. Generality refers to the capability to generate motion plans for a wide range of tasks. It is the most important of our 3 evaluation criteria. Because motion generation uses search, it can in principle generate a motion plan for every feasible task. The robot can thus reach for different goals on the table and generates motion plans for different table heights just as well. Dynamic movement primitives also generalize within a specific task context, such as reaching for different goals on a table. For this task, however, the primitive fails to generalize to a lower table, as it produces an awkward-looking motion and causes self-collision. In this work, we have performed an empirical quantitative analysis of the advantages of motion generation and motion recall. We have found that motion generation, as implemented with lazy RRT, leads to high variability in movement, high computational load, yet is very general. Motion recall, as implemented with dynamic movement primitives, leads to low variation, negligible computational cost, yet, by design, is limited to specific tasks. Our conclusion is therefore that these approaches complement each other well. This suggests further comparisons and the integration of both approaches for everyday mobile manipulation.